Yeah, good day everyone. You are welcome to Access Point Academy video lecture series, subject physics, and today we want to unravel dimension analysis. Okay, so dimension is one of the most important aspects of Newtonian physics. Physics that has to do with the scientist Sir Isaac Newton. So dimension has very numerous benefits. Help us to reveal the authenticity of a given formula by comparing the parameters at the left hand side of the equation to those at the right hand side of the equation. For instance, if we say energy is equal to the product of mass, specific heat capacity, and temperature change, we should be able to prove that truly that energy is equal to mass. We should be able to prove that truly energy is equal to specific heat capacity. Also, we should be able to prove that energy is equal to temperature change. So that is what dimension will teach us. Dimension also shows the genuineness of a given formula to let us know if a formula is correctly really or if it is not correct. So dimension will help us to show whether a formula is correct or is not correct. So dimension will do that. So it shows the authenticity, it shows the genuity, it shows how important a formula is. If kinetic energy is equal to half mv squared, you should be able to prove that the left hand side of the equation, which is kinetic energy, is equal to mass multiplied by the square of velocity. So dimension will teach us that. Dimension shows genuineness and authenticity of a given formula. So now, we now have in this table, the table below shows the dimension of some quantities. The table below gives the dimension of some quantities. Now these are quantities, they have their dimension. Length, the dimension for length is L, capital L. Breadth is L, height L, radius L, diameter L, displacement L, distance L. Mass is M, the dimension for mass is M, the dimension for time is capital T. An electric current is either A or I. Okay, it depends. The dimension for electric current is either A or I. The dimension for mass is capital M and time is capital T. So now we need to do some illustration. Now there is a question here which says the dimension for deduce the dimension for the following quantities. So they want us to deduce the dimension for the following quantities: area, volume, density, speed, velocity, acceleration, force, pressure, moment, impulse, work done, power, electromotive force, EMF, then surface tension. We have about 14 of them. We need to show their dimension. Now, to answer those questions, we're going to learn two things. We're not only going to show the dimension, we will also tell you the formula used for calculating all those quantities mentioned above. So you're learning two things simultaneously. So you are learning two things here, formula and dimension. Okay, so now the first one in the question, area. So what is the dimension for area? How do we go about that? So now area, the formula for area is length times breadth. And up there, we said the dimension for length is L. That's it. Dimension for L, for length is L, and dimension for breadth is also L. So therefore, we can now have that length multiplied by breadth, which is L multiplied by L squared. So that gives us the dimension for area. So the dimension for area is L raised to the power of 2, L squared. Now, the second question there is volume. Volume is length times breadth multiplied by height. And the dimension for length is L. The dimension for breadth is L. The dimension for height is also L, as it is revealed in this table here. You can see that the dimension for length, for height, is L. So length, breadth, and height, they have the same dimension, L times L times L. Then you square, that will be L raised to the power of 3. Okay, L cubed, L raised to the power of 3. Now the next thing they ask us to do is density. Okay, so the formula for calculating density is mass over volume. Mass divided by volume. And we said earlier up there that the dimension for mass is capital M. Okay, so we know the dimension for mass, so we're going to write it in the place of mass. Mass dimension is M, and the dimension for volume, which we've done before in question number 2, L to the power of 3. So over M over L to the power of 3. So which is equal to ML raised to power minus 3. Okay, ML raised to the power of minus 3. So now the L is going to go up. So it was initially at the numerator position. When it gets to the it was initially at the denomination position, and when it gets to the numerator in fraction, then it becomes L raised to the power of minus 3. So that is indices. Indices is what was done here. The L raised to the power 3, when it changes its position and move up, is going to be minus. You introduce minus to it and be minus 3. That is the knowledge of indices. Now next is speed. The formula for calculating speed is distance over time. Distance over time. And distance, the dimension, which we learned earlier, is L. Dimension for distance is L, and the dimension for time is capital T. So we can now write that distance is equal to length over time, so L over capital T. So now when this T go up like we did for density, so the T is going to go up and it will become LT minus 1. So this is the dimension for speed. The same thing as displacement. Now displacement, velocity is equal to displacement over time. Okay, the dimension for displacement is equally L, as it is on the table there, divided by time, which is T. So you have LT to the power of minus 1. Okay, so we need to note speed and velocity are dimensionally the same. Can you see that the dimension for speed is LT minus 1, and the dimension for velocity is LT minus 1 as well? Okay, they have the same dimension, they have the same SI unit. Okay, but one is scalar, the other is vector. Speed is a scalar quantity, while velocity is a vector quantity. Now the next one is acceleration. Now, what is the formula for acceleration? If you want to calculate acceleration, the formula for calculating acceleration is velocity over time. Okay, and we know what the dimension for velocity is. This is velocity. Okay, so LT minus 1. So we place that LT minus 1 in the position of velocity, LT to the power of minus 1 divided by time, another time again. This is T. Okay, so you now take them everything to indices form. This is LT minus 1. Then when this T go up, it will now turn to T minus 1 again. So initially we have LT minus 1 multiplied by T raised to the power of 1, because this one is going up, indices. So you now have LT minus 1 minus 1, that is minus 2. So the dimension for acceleration is LT minus 2. Okay, I hope that is taken and very clear. Let me quickly revamp that. Let me quickly re-explain that. So acceleration formula is velocity over time, which is equal to velocity is LT minus 1, which we calculated up here. So you don't need to derive it, you can just bring it from there, put it in the position of velocity, and time is capital T. Okay, so on going up, it has 1 raised to the power of 1. So now when it goes up, it will now become minus 1. So you now have your LT minus 1 minus 1. That will be LT raised to the power of minus 2. Now, also, force is equal to mass times acceleration. Okay, force is equal to mass times acceleration. And force, which is equal to MA. So now MLT to the power of minus 2. So the dimension for mass is capital M, and the dimension for acceleration is LT minus 2, as we did in question number 6 above. So just bring down the M, then LT minus 2. That is the dimension for force. Now next is pressure. The formula for calculating pressure is force over area. Okay, and what is the dimension for force? This is it, mt to the power of minus 2. So mt to the power of minus 2. And dimension for area is L square, which we did. That was the first question we did. This is the dimension for area, L square. That is L to the power of 2. Okay, so we can cut one of these L. We cut one of the 2 here. Okay, so we are now left with mt to the power of minus 2. Then this one has now become ordinary L. Initially it was L square, but we have cut. So now this L will now go up. We don't always leave dimension like this in physics, so everything must be on the same line. So now M, okay, which is this M, this L will go up. It will become L to the power of minus 1, then T to the power of minus 2. So that is the dimension for pressure, ML to the power of minus 1, then T to the power of minus 2. Now next is moment. The formula for calculating moment is force times distance. Okay, and force, the dimension for force, which we've done earlier, MLT minus 2. So you can just bring it down and write MLT minus 2, okay, multiplied by distance. The dimension for distance is L. So now it will now be M, bring it down, L times L, that is L square. That is how we have our L square there. Then T to the power of minus 2. So this is the dimension for moment. Okay, ML square T to the power of minus 2. Then next is impulse. Impulse is the product of force and time. And what is the dimension for force, which we've done earlier? So force is MLT minus 2 multiplied by time, which is T. Okay, so now ML, so T to the power of minus 2 times T to the power of minus 1. So now you bring down the ML, which is this. Now T is here, T is here. So you pick one of the T. You pick one, raised to the power of minus 2 plus 1. This is indices, pure indices there. So it will now become minus 2 plus 1. That will be minus 1. So the dimension for impulse will now be MLT minus 1, because minus 2 plus 1 is minus 1. So the dimension for impulse is MLT minus 1. Now we move to the next one, which is work done. Work done is equal to the product of force and displacement. And force is MLT minus 2 multiplied by length, displacement, whose dimension is L. So now it now be L times L square, then T raised to the power of minus 2. So M is always coming before L, and L will come before T. It is written in MLTs as a standard value. So they ask us to note that work done and moment are dimensionally the same. Good. Now, where is the dimension for work done? ML squared T minus 2, and moment as well, ML squared T minus 2. So meaning that work done and moment, they are dimensionally the same. They have the same dimension. Now, next is power. Power is the ratio of work done to time taken. That is work done over time. Okay, now when you check up, we have done the dimension for work done somewhere else up here. So the dimension for work done is ML squared T minus 2. So you just write it directly in the position of work done, ML squared T to the power of minus 2 over T. Okay, so now we now bring this time, we take it up. So when it goes up, it's going to be minus 1. So now it will therefore be ml squared t to the power of minus 2 t to the power of minus 1. So we now have ml squared t to the power of minus 2 minus 1. So minus 2 minus 1 is minus 3. So the dimension for power is ml squared t raised to the power of minus 3. Okay, so that's justify for power. Now the next is electromotive force. Very, very important for you to note. Okay, now for electromotive force, the basic formula for electromotive force is work done divided by charge. And work done, the formula for work done is force times distance. Okay, over the formula for charge is IT, that is current multiplied by time. So you write the dimension for force, mlt minus 2 times distance L divided by current. The dimension for current, we said, is either A or I. So in that wise, we are using I, like we said, dimension for current. So we now proceed, and we have that dimension for current, which is T, and dimension for time is, dimension for current, which is I, and dimension for time is T. So we now let each and this denominator, we bring them up. So now what we have up before was mlt, okay, raised to the power of minus 2. So now we bring these two L's, L multiplied by L, that is L square. So we have ml square, then T raised to the power of minus 2 before. This one will go up, it will become minus 1. Okay, minus 2, minus 1, those are the T's. So minus 2 minus 1 is minus 3. Y current is also going up, so it will be I to the power of minus 1. So the dimension for electromotive force is ml square T raised to power minus 3, I raised to power minus 1. Now, the last one there, I think, is surface tension. So surface tension is the ratio of force to length, force over length. That is surface tension. And force is MA over length L. So force is mlt minus 2, and length is L. So L will cancel out L. The L have cancelled out, and they are out. Then what you have left is mt to the power of minus 2. Okay, so that is the dimension of surface tension. So there could be some question that has to do with analysis. Okay, so like we have a worked example here. They said the value of x, y, and z respectively in the expression m raised to power x, l raised to power y, and t raised to power z for the dimension for the universal gravitational constant G are. So we are meant to find x, we are meant to find y, and we are meant to find z. So how do we go about that? Now, this is what we do. From Newton's law of universal gravitation, F, the force of attraction, is equal to G mm divided by r square. Okay, so now on cross multiplication, when we cross multiply, we have G mm equals fr fr square. Now we need to make this gravitational constant G our subject of formula for us to get its dimension and know the respective value of x, y, and z. Okay, so now we divide both sides by by the masses. This side as well, we divide by the masses. So this cancel out this. Okay, so we are now left with our G equal to fr square divided by okay, so that continues here. So now what is the dimension for force? Force is mLt minus 2. You can check up there. Multiply by this r, which is the radius. Dimension for radius also we learn, and we said is L. The dimension for radius, which is r, is what? Is also L. Okay, so we now go back to the question and put its dimension. So now the dimension for force, we've written it. Then we are following this. Dimension for radius is L, but on the radius there is square. So therefore your L will become L square divided by the two masses m, okay, such that this m will cancel out one of this m. So this m that is at the denominator will go up. So therefore it become m raised to the power of minus 1, because it's going up. Then this is L raised to power 1 multiplied by L raised to power 2. L raised to power 1 multiplied by L raised to power 2. Then the t will always come last. T multiplied by t raised to power minus 2. So you are now left with m raised to power minus 1, L raised to power 1, that will be plus 1 plus 2, that is 3 indices, then t raised to the power of minus 2. So we can now compare this dimension for G with what we are asked to do in the question, m raised to power x, L raised to power y, and t raised to power that. So we now have m raised to power x, L raised to power y, and z raised to power z. So now, how do we get that definitely? Now, we compare m to m. M is raised to power minus 1 is equal to mx. Then L is raised to power 3 is equal to ly. Then t is raised to power z is equal to t raised to power minus 2 is equal to t raised to power z. So now we can now compare and see. Therefore, now our x is equal to minus 1. Compare the So on the power of this m minus 1, on the power of this x is that. So x is equal to minus 1 because the m will cancel out. Then the same thing, our y will be equal to 3. Because this y and y will cancel out. We have y equal to 3. So y is equal to 3. Then for the t, okay, this t is equal to t raised to power minus 2. So that z will therefore be equal to minus 2. So those are the respective values of x, y, and z. So you can say x, y, and z are minus 1, 3, and minus 2 respectively. Okay, so that justifies that we've gotten the respective values of x and y. So now the next question says, at what respective values of x, y, and z could the unit of force, the newtons, be dimensionally equivalent to m raised to the power of x, L raised to the power of y, and t raised to the power of z? Good. Now we need to solve that as well, like as we actually solved for the one above. So how does that go? Right, that force, which is equals ma, and that the dimension for mass is and acceleration is LT to the power of minus 2. Okay, so we now compare this with this question, with the ones we have in the question. So we compare. On comparing, we have m to the power of x, l to the power of y, and t to the power of z. So you take them one by one. This m, if you didn't see any power on it, so just know that the power on it is 1. So you compare it with x, m raised to the power of that. Then this l as well, there is nothing on it, so you should know that it is 1 that is there. So you have l raised to equal to l raised to the power of y. And at the same time, for t, this t has minus 2. You write the minus 2 equal to t raised to power z. Okay, so you can now start comparing, and you will see that the power of this is 1 and the power of this m has x. So that is x is equal to 1, y is equal to 1, and z is equal to minus 2. So the respective values of x, y, and z are 1, 1, and minus 2. Okay, so that has actually justified that. So that is dimension analysis. Okay, so we're going to call it quits for dimension. So we meet in the next video class.